let's start with today's class. Now, today, as we have already planned, we start with the new chapter. Remember, so far in this unit, we are in the second unit of the course, and in this unit, we are talking about sound producing instruments. And one class of instrument we learnt which belonged to the musical class category, and that was a woodwind instrument. Now, of course, the most important sound producing instrument for us is human voice or human vocal cord or speech production. We are going to focus on that in this class today. Remember, there is a separate body of study for singing, and the separate is speech. Although the basics are same, but human vocal behavior differs a lot when you are singing and when you are talking. We are focusing on speech right now. So, speech production is the central idea in this chapter. We are basically going to look at vocal tract, which is a biological part of human being, but we are going to look at from the physics perspective, vocal folds, which are the seat of voice formation, vocal formants. These are the three concepts that I'm going to take up in this class as the base. So what is vocal tract? We are all familiar. Vocal tract expands or extends from human mouth and it goes below somewhere in the neck, somewhere below the neck region. Towards it goes to the lungs. Here is the mouth. The nasal or nostril cavity is a part of the vocal tract. So both the things are together. So main source of vibrations or main seat of vibration is there in the this part of the entire vocal tract, which is called as vocal folds. So this is the vocal folds. The presence of the vocal fold sometimes is in some humans is shown by a small rising of neck in this section, which is normally referred as Adam's apple or thyroid cartilage. You make a sound of say zzz, keep your finger on your neck and you would realize the vibrations of the vocal folds. So it's very simple to locate. You can put a small mirror, push a small mirror in your mouth and reflect its image on a camera also. So that's the seat of source of vibrations, vocal fold. We'll come to it in a while. And there are different parts of the vocal tract which modulate the basic vibrations which are produced by vocal folds. These parts are whatever they are away from it or above it, like larynx, pharynx, oral cavity, which includes your lip, mouth, tongue, teeth, etc., and your nasal cavity, which is this one. Air from the lungs generally is pressed at a higher speed in the vocal folds. As the speed increases in this part, when you have to talk, when you have to speak, when you have to sing also, the, the lungs will push the air at a high speed through the vocal folds. Remember, if it is not done at a high speed, then it doesn't happen. So that is what is the difference between being quiet and talking. When you are quiet, the air is still flowing through this part, going to the lungs and coming out when you are breathing. Okay, so it does happen. The air, if you're breathing by nose, the air will travel this passage and come to this and goes to the lung. It doesn't affect the vocal folds. You don't talk when you are quiet. But when you intend to talk, at that time the lungs pushes the air at somewhat a higher speed through the vocal folds. As the air passes at a high speed, if you recall the Bernoulli's principle, it it is accompanied with a drop in the pressure. So the pressure drops in the vocal folds and in this region, and as the vocal folds, as the pressure drops, the vocal folds, they tend to come close. They are valve-like openings on both sides. They tend to come close and tend to block the tract at this point. As they tend to block the tract at this point, the pressure in this region, that is just below the vocal fold, that is called trachea, the pressure in this region increases. As the pressure in this region increases, you will find uh, that a high pressure in this region will push the vocal folds to open once again. As the vocal folds open, the air escapes at a very high speed towards the upper section, and once that happens, again the pressure drops and the vocal folds close. So this vibration, there's a vibration like mechanics now. The alternate opening and closing of the vocal folds gives the vibrations. The process repeats several times a second. We'll come to the more details on that in a while. And how fast or slow it vibrates, it is determined by the tensions in the muscles, tensions in the muscle, and of course the mass of the muscles and size of the muscles vary from in various ways. It varies by gender, from male to female. It varies by age, from childhood to the grown-up persons to elderly, and therefore that determines the bass frequency produced by the vocal folds. Here is a mechanical model of the vocal folds. If some of you are interesting for a project work, maybe you can think about it. It is consisting of one main tube with a pump-like structure which will apply the force. Then it goes to one cavity, and then it goes to one mouth cavity and one nasal cavity. This is the pharynx cavity. Then you can control these three cavities suitably to see what is the output. This is one of the primitive models. There are more advanced models and more detailed models. We will talk about them in the next class. Coming back to the vocal tract, some of the observations, some of the experimental observations are straightforward. Vocal cord or vocal tract is longer and heavier in male than in female. So on an average, it's longer. Remember, longer the length, the lesser is the resonant frequencies. So the male voice is generally at a lower resonant frequency and it is more bassy than the female voice. During normal speech, vibration rate may vary by 2:1. That means normal talking, the frequency is not constant. Sometimes it increases, sometimes it decreases. General ratio is 2:1 or 1 octave. During singing, it can change by 4:1, that is 2 octave. That is what we said. I told you in the beginning that singing is a separate, the behavior of vocal fold while singing is a separate case study. So while singing, it can change by 4:1 or 2 octave, and maybe there are some exceptional singers which can go up to 3 octaves. That is in a third one, which is normally the lowest octave. Now come back to the vocal folds. So the behavior of vocal folds, these are the sketches of the vocal folds. It's here. It has two openings through which the air will pass. If you look at the cross section, it looks like this. This is a closed vocal fold. So the two surfaces, they come close and block the airflow. And this is the open vocal folds. So sources of vibrations are vocal folds. Closed vibration cuts off the air's sudden openings like H or idiot, those sounds. I mean, these are the sounds if you make, uh, then it happens that it closes suddenly. I'm not a speech scientist, so my pronunciation can be poor also. So you just have to try your own pronunciation and experience. So if you say the word idiot, many a times you will feel some sort of restrictions or constriction in your neck. That is what is the closing of the vocal folds. It's completely open when you pronounce the letters like S, sh, 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 or F. So it's completely open. Now, these are the one mode, but then it can be partially closed also. And therefore, the modulation of airflow is wonderfully done by the vocal folds. So, vocal folds, as I said, they can be completely open, completely closed, partially open, partially closed. They can vibrate at different frequencies to give you a variety of frequency outputs. They modulate the airflow brilliantly. And the rate of vibrations, as we have said, is determined by the mass and the tension. It is typically in a young male 110 hertz and 220 hertz in the female and 300 hertz in the child. So, children normally the frequency is very high, the base frequency. Now there are various modes of vibrations of the vocal folds. As I said, one mode is that it opens and closes completely. It's completely open and completely closed. You say one letter or one sound, one syllable, one phoneme at a time, and it is completely open or completely closed. It is it is half open. So breathy voice like no. If you say no, then in that case it is just half open. The third mode is that a minimum air passage in the short puffs result in a creaky sound as you are lifting a heavy weight while talking. So something like that. If you are lifting very heavy weight and also talking, the way you talk, this is the third mode of vibration. There's another mode of vibration which is used, which can describe singing, not the part of discussion right now. Now, how does the airflow varies when it opens, when the folds open and close? So when the folds open, typically the volume velocity rises. On this graph, on the y-axis, have got volume velocity, cubic centimeter per second of air, and on this we have time. So this is a typical behavior. As I said, a normal, comfortable behavior in for a human male. You can see here that the for the around 3 millisecond or slightly over 3 millisecond, the volume velocity goes on increasing. But as the airflow increases, the volume velocity increases, you know that the pressure will drop. As the pressure starts dropping in this region, a point comes when the vocal folds close down, and when they close down or start closing down, when they start closing down, the volume velocity decreases. As the volume velocity decreases, it on almost around 7 millisecond or maybe in around slightly over 7 millisecond, it completely closes down. So that completes one cycle of vibrations. Then this will keep repeating, because what happens, I have already explained, once the volume velocity is zero through the vocal folds, the air pressure in the trachea increases, and that forces the the tract to open once again and increase in the volume velocity further. Typically, it has an 8 millisecond repetition time and it keeps repeating one after the other. It's around 125 hertz. So you can look at this diagram. This will keep repeating at 185. This is like a triangular waveform. If you notice carefully, it is like a triangular waveform and it has harmonics present. So you can predict or you can find out what are the harmonics present by using an RTA many real-time analyzer. It's called real-time analyzer, RTA softwares available on your phone. You can just download. I'm going to show you one video and maybe um, you can take help from that. But RTA real-time analyzing softwares are freely available. You can download. There are many good softwares. You can use them to analyze voice, analysis of human voice for your projects. So here are the frequencies which are higher frequencies or frequency spectrum of these puffs. Very high frequency towards 125, but as you go in the higher multiples, the amplitude slowly drops. We are coming back to this in a while because this will help us to make the sound more plausible for articulation of speech, because these are the basic frequencies. All this will produce is some or kind of noise. So this is just a basic vibration, but human voice is more articulated. We don't just produce these kind of noises, but we talk a lot. We'll talk in different syllables, vowels, etc., languages, words. So it's much more complex. So in the remaining part of the lecture, I'm going to bring how these basic vibrations can be modified into various types of speech. So the frequency in the vocal formants. So let's talk about vocal formants. Formants are the dominant group of frequencies which are present in human voice. That is the vocal formant, dominant group of frequency. Frequency is determined by the tension in the muscles, as we have already seen. Higher the tension, higher the tension, more is the frequency that we have already seen. Amplitude or the loudness is determined by the rate of flow. Larger the volume flow, more is going to be the amplitude. The length of the tube is around 17 to 18 centimeter. From length of the tube is measured from the vocal folds to this point. So around 17 or 18 centimeter. And the resonant frequencies are 500, 1500, 2500, 3500 hertz. These are the basic resonant frequencies where the output is going to be strong enough. So do remember that at 125 hertz, the out of the vibrations of the vocal folds, the output is not that strong. The output undergoes under resonance at these frequencies. So do remember these frequencies: 500, 1500, 2500, 3500, etc. You can use these frequencies. We are going to use these frequencies and create some sound artificially. The principal vocal formants are around these frequencies. So that's very important part. Lips are used to control the lowest formants. Now, although this tube acts like a resonator, the resonant frequencies of the tube can be altered. And one of the main place where this alteration takes place is called mouth. So lips are used to control the lowest formants. So you can move your lips up, down, open, close, etc. Higher formants are affected by tongues and other parts. You can actually change the length also. For example, if you protrude the lips out and say something, the length slightly increases. When the mouth is closed, nasal cavity determines the formant. So if you close the mouth, the formants are determined only by the nasal cavity. Only nasal cavity will determine. Now nasal cavity does not have any movable structure, and the shape of this cavity does not change significantly, it remains fixed. Therefore, you cannot do much with nasal cavity apart from making some noises like something like that. You cannot do much over here because you can do lot with the lips. Average male can change the first formant frequency by 1000 Hz and second formant frequency by 2000 Hz. This has been observed. These are the positions of the lips for the various sounds: E, E, A, U, O, I. So these are the different ones. Each sound is called, normally the speech scientist, each sound, they call each sound as phonemes, and one or more phonemes combine to form a syllable. Not much of our use, but what is of our use is uh, vowel sounds are always produced in vocal folds. So the five vowels of English, A, E, I, O, U, these are all sounds which are produced in vocal folds, and consonant sounds may be either produced in vocal cord or uh, sometimes in the other part vocal folds, or sometimes in the other part of vocal cords. I would recommend you people to download an RTA, real time analyzer software, and speak into it, maybe one word at a time, and figure out what are the dominant frequencies. So vocal formants are can be understood very easily. Pitch and intensity is determined by the vocal folds. Spectrum quality is strongly shaped by the vocal tract, as we have seen. Pitch and intensity are the basics. So the vocal folds acts like a seat of vibration. They generate the sound, let that sound spread out. But spectrum is strongly shaped by vocal tract. What kind of final spectrum is arising? That is strongly shaped by vocal tract. Then, apart from the vocal tract, part of the vocal tracts which shape the spectrum of pharynx, mouth, and nasal cavity, shaped by tongues, lips, and palate. So, here is an example which can be used in synthesizers to create artificial speech. Examples are very straightforward. These are the basic vibrations of the vocal folds, as we have seen, 8 millisecond. This is their spectrum. We have also seen. Now the spectrum can be multiplied by a filter function. So this is a filter. Now this modulates the amplitude. So when you multiply this to this, you get this one. You can see that some frequencies are amplified like this one, and some frequencies like this one is suppressed. So if you amplify some frequency and suppress some frequency, again amplify some, then what is a diminishing spectrum over here can be given different shapes. Once these shapes are given, you can generate the complex waveform, and that complex waveform forms your actual speech. So this kind of things happen in human voice. As a proof of it, we can actually synthesize everything in a synthesizer. That's how the artificial speech is synthesized. If you if you can recall Dr. Stephen Hawkins, he always spoke using a synthesizer. So let me show you a small video to end today's class. Please look at it carefully, how this person creates a basic vibrations and then modulate it up and down to create different kind of speech patterns.
Hello, and welcome to my brief explanation of formants. Formants are one of the harder concepts to grasp in acoustics. They're basically ranges of frequencies that are amplified by the shape of your vocal tract, the shape of your throat and mouth, that give your particular voice its distinct characteristics, and also are responsible for vowel sounds. So, in theory, a voice produces an infinite number of formants, but only 4 or 5 are really relevant to the way we hear things, because higher ones are just out of the range of human hearing. And the most important are the first 2 formants, the lowest 2. Those are the formants that are responsible for vowel sounds, and 3 and up are just responsible for the color of your particular voice. So before I really start talking about formants, let's just go over what you're seeing here in front of you. This is a graph of the sound spectrum, all the sound that you're hearing.
By the way, what he is showing is an RT, a real-time analyzer. So what this is doing is, if you look at it carefully, on the y-axis it is the amplitude, and on the x-axis it is the frequency. So he has different frequencies starting from 50 hertz to 20,000 hertz, 12,000 hertz, maybe. Yeah. And as he speaks through it, the software analyzes the different frequency components and their amplitudes, and produces it on the screen for him. So let's go ahead with this.
About formants, let's just go over what you're seeing here in front of you. This is a graph of the sound spectrum, all the sound that you're hearing in this video, all the sound that's going through my computer is being displayed on this graph. Low frequencies over here and high frequencies over here. The louder a particular frequency is being played, the louder the spike, or the higher up the spike at that point will be. So you might be thinking, humans can only produce one pitch at a time when they speak or sing, right? So why am I seeing frequencies all over this graph? Well, any complex sound, like a human voice or an instrument, produces a bunch of what are called overtones. And I won't be getting into overtones too much for now, but suffice it to say that overtones are higher frequencies than a fundamental note that you're singing that go all throughout the sound spectrum. Your voice also produces some white noise, like your consonants, like S's and T's. There's no actual notes, but there's still sound. It's called noise. And just air passing through your vocal tract also produces some noise. So with that little explanation, let's get into what exactly formants are. I can show you where the formants in my voice are just from this graph here. So let's say, let's take the vowel e as an example. So so there's a spike in frequencies around a little less than 2,000 hertz, and another one between like around 600 or 700 hertz. And to show you that that is what is making the vowel sound, let's take that note that I was singing, and I'm playing it on a synthesizer now, and I'm going to amplify the frequencies in those areas, and it will sound like the vowel sound that I was saying. So let's amplify at around 600, and we also said a little less than 2,000. Kind of sounds like the vowel e. We can do other vowels in this way. Like if we move the second formant down nearer to the first, we get an ah. We can move the first formant down and we get like an oo. And then that's kind of like I or E. So as you can see, vowel sounds are produced by 2 frequency bands that are amplified by your vocal tract. And I can show you different vowel sounds with my own voice too. You see those 2 resonances are just moving around in the sound spectrum, and that's what's changing when you change vowel sounds. And basically, those are formants. That's what the concept of formants is. And as I was saying earlier, the higher formants just give your voice its own particular color. We can add those into our synthesized voice as well. So let's make ah again, and we'll add 2 higher frequency formants, and it sounds like this. Just gives it a little more color in the high end. There's without. And begin with. So different people are going to have different higher frequency formants, and that's why different people's voices sound different. So it's worth noting that your vocal tract will resonate in the same way no matter what note you're singing. That's why you can say a vowel, like let's say eh, and I'm going to change notes now. Eh, and it still sounds like eh because the formants haven't moved. So let's play ah on our synthesizer, and I'm going to change notes. It still sounds like ah because the formants are in the same place in the sound spectrum, even if the note that's being played is moving. And that means that you don't even have to be singing a note for formants to act and create vowel sounds. That's how whispering works. You can see the formants are around 1,000 when you say ah, and that works with whispering too. That's what whispering is. You pass noise through your vocal tract, and the formants in your voice filter it in the same way. So one other concept that's worth talking about is the concept of vocoding. Vocoding is when a computer looks at...
Okay, so I hope that makes it very clear that how this interaction of air passes through the vocal folds and subsequent modulation by the vocal tract produces a very articulated vast spectrum of speech. Now you can do this experimentation on any software further, and we can stop here in this lecture. I will be available in Google Meet for any discussions if needed. In next lecture, we are going to talk about vocal cord models and how do they predict the behavior of the vocal cord further. So we can stop here. Thank you.